To analyze system performance, I started by opening Performance Monitor from the Start menu under Windows Administrative Tools. Once it was open, I selected Performance Monitor from the left pane and clicked the Add button at the top to choose key metrics like processor time, memory usage, and disk I/O. After adding the metrics, I observed the real-time data displayed on the graph. I monitored the system for a while, carefully watching for any anomalies, such as spikes during peak usage times. Everything appeared normal, with no unusual findings during this period. This process gave me a clear view of how the system was performing. To analyze system performance using Resource Monitor, I started by opening Task Manager and navigating to the Performance tab, where I clicked on Open Resource Monitor to launch the tool. Once the Resource Monitor interface appeared, I examined the detailed real-time data across several key tabs, including CPU, memory, disk, and network. In the CPU tab, I observed the active processes and their associated resource consumption, looking for any unusual spikes or processes consuming an abnormal amount of CPU time. Next, I moved to the Memory tab, where I reviewed memory usage for individual processes and checked for any instances of excessive consumption that could indicate a memory leak or inefficient resource management. In the Disk tab, I monitored disk activity, focusing on processes with high read or write operations that might signal potential bottlenecks or performance issues. Finally, I analyzed the Network tab to identify processes with significant bandwidth usage, which could point to network congestion or unexpected activity. Throughout the monitoring process, I carefully documented my observations, noting that no anomalies or unusual behaviors were detected across any of the resource categories. The system's performance remained stable, with all processes operating within normal parameters, and no immediate actions were necessary to optimize resource usage. This thorough examination confirmed that the system was functioning efficiently and provided valuable insights into resource allocation and system health. To evaluate system stability using Reliability Monitor, I began by navigating to the Control panel and selecting Security and Maintenance. From there, I accessed the maintenance section and clicked on View Reliability History, which opened the Reliability Monitor tool. This tool presented a graphical timeline displaying the system's stability index over a period of days, highlighting any system warnings, errors, or critical failures that had occurred. I started by examining the overall stability graph, looking for any sudden drops or patterns that might indicate recurring issues. Each point on the graph represented a specific day, and I clicked on recent entries to view the associated system events in detail. The detailed view provided a breakdown of informational events, warnings, and critical issues, allowing me to understand the context and nature of each event. I focused on identifying any recurring problems, such as frequent application crashes, system hangs, or hardware errors, which could indicate underlying issues that might need resolution. For each event, I analyzed its description, including timestamps and possible causes, such as software conflicts, driver issues, or hardware malfunctions. Explain the occurrences. After a thorough review of the timeline and event details, I found that the system had been stable except when the server was turned off in the VM, with no significant warnings, errors, or critical failures recorded in recent days. The absence of recurring issues or anomalies suggested that the system was functioning reliably and did not require any immediate intervention. This evaluation provided a comprehensive assessment of system stability and confirmed that the system was operating within normal parameters. The reliability monitor proved to be an invaluable tool for understanding the system's health and identifying potential issues before they could impact performance. To create and analyze a data collector set, DCS, for monitoring system performance, I started by opening Performance Monitor and navigating to Data Collector Sets, selecting User Defined. From there, I chose New and then Data Collector Set. I named the set Server Performance DCs to align with the task's focus and opted to create it manually using the Advanced option. In the configuration settings, I carefully added the necessary performance counters, including CPU, memory, network adapter, and disk, to ensure a comprehensive view of system resource usage. Each counter was selected to monitor specific aspects of system performance, such as processor utilization, memory consumption, network activity, and disk operation. Once the data collector set was configured, I saved the settings and started the collection by right-clicking the set and selecting Start. To capture meaningful data, I allowed the DCs to run during peak operational hours, ensuring it could record performance metrics under realistic workload conditions. This period of monitoring was critical to understanding the system's behavior when it was under significant stress or demand. After the collection period ended, I navigated to the Reports section in Performance Monitor under User Defined to view the results generated by the data collector set. The report provided a detailed analysis of resource usage, with graphical representations and data points for each counter. I carefully reviewed the report, analyzing trends and looking for any anomalies or areas of concern, such as high CPU usage, memory bottlenecks, disk activity spikes, or network congestion. However, the data indicated that the system was operating within normal parameters during the observation period, with no significant issues requiring intervention. This process not only confirmed the system's stable performance, but also provided valuable insights for ongoing monitoring and resource management. analyze network activity using Packet Monitor PKTMon, I started by opening command prompt with administrative privileges. Although the system had no internet connection during this task, I executed the necessary commands to simulate the process as if a connection was present. First, I initialized Packet Monitor by running the command pktmon to verify the tool's availability and ensure it was ready for data collection. I then executed the correct command to start capturing network data, ensuring all traffic and potential network interactions would be logged for it. After allowing the capture process to run for a sufficient period, I stopped the monitoring session by using the pktmon stop command. This action saved the captured data into a report file for further analysis. Despite the absence of an active internet connection, the file contained any logged information related to network interfaces and attempted activity during the capture window. I proceeded to analyze the report, focusing on identifying any packets that might exhibit significant delays, errors, or irregularities. Since there was no network activity due to the lack of an internet connection, the captured data showed no unusual findings. All metrics and logged information were consistent with a system that had no active network traffic, confirming that the process worked as expected under these conditions. This exercise demonstrated how Packet Monitor can be effectively set up and used to diagnose network issues, even in environments with limited or no connectivity. To simulate network troubleshooting tasks in a no-internet environment, I began by addressing a DHCP troubleshooting scenario. I configured the DHCP server scope to run out of available IP addresses, effectively simulating a failure to assign IPs to new devices. After setting up this condition, I attempted to connect a device to the network, which failed to obtain an IP address as expected. To investigate the issue, I accessed Event Viewer, navigated to Windows logs and selected System. Within the logs, I reviewed entries related to DHCP activity and found evidence of lease conflicts and scope exhaustion errors. This confirmed that the DHCP server was unable to assign IPs due to the scope limitation, demonstrating how to diagnose and verify such issues using Event View. For the root check, I attempted to use the traceit command with www.sheridancollege.ca to trace packet routes. However, since there was no internet connection, DNS resolution failed and the domain name could not be resolved. To overcome this, I used the internet outside my virtual machine to manually look up the IP address of the server associated with www.sheridancollege.ca. With the IP address in hand, I returned to my VM and attempted the traceit command using the IP address directly. Predictably, the trace could not proceed beyond the local network, reflecting the lack of internet connectivity. This exercise highlighted how external tools and manual DNS lookups can supplement network troubleshooting when connectivity within the primary environment is unavailable. Both scenarios effectively demonstrated key troubleshooting methods, showcasing how to work around limitations and use diagnostic tools to analyze network behavior, even in environments with restricted connectivity. configure and use the Active Directory Add Recycle Bin, I first enabled the feature to ensure deleted objects could be recovered. Enabling the Add Recycle Bin requires access to the Active Directory Administrative Center ADAC. After launching ADAC, I navigated to the domain node and selected Enable Recycle Bin from the Tasks pane. This step was confirmed through a prompt indicating that enabling the recycle bin is irreversible. Once this was completed, I restarted the Active Directory Domain Services Manager to apply the change. Next, I tested the functionality by navigating to the Deleted Objects container in ADAC. Initially, it took some time to familiarize myself with the interface and locate the Deleted Objects section. Once there, I confirmed that the container includes deleted items such as users, groups, and organizational units. To demonstrate the recovery process, I deleted a test user account. Afterward, I navigated back to the Deleted Objects container, where the deleted user was listed along with details like the deletion timestamp. I highlighted the options available for recovering the deleted object, such as restoring it to its original location or to an alternate location within the domain. This process demonstrated the practical use of the Add Recycle Bin, providing a straightforward way to recover accidentally deleted objects and reinforcing the importance of enabling this feature for effective Active Directory management. authentication logs, I started by attempting to generate a failed login event in the Active Directory controller. The plan was to log into one of the domain systems with an incorrect password to create a record of the failed login attempt. This event would typically be captured in the Active Directory controller and logged under Event Viewer greater than Windows logs greater than security. However, due to the configuration of my environment, where I did not use a different system to perform the login attempt, the failed login event was not logged as expected. This outcome highlighted the importance of ensuring proper domain system interaction when testing authentication events. The absence of logged events also served as a reminder to verify that auditing policies are appropriately configured to capture such activity, including enabling auditing for account logon events and ensuring domain controllers are correctly receiving log data from domain systems. Despite the inability to generate the intended log, this exercise provided valuable insight into the prerequisites for successful authentication log reviews and reinforced the need for accurate configurations in simulated environments.